Okay, take two. Supersonic phenomena of matter. So I put redundant at the end there. Why is that redundant? Well, it's because without matter, some sort of stuff with little particles that all have some sort of relationships with each other, you can't really define the speed of sound. I mean, you can, but it won't be truly the speed of sound. It would be a field different than the kind of supersonic field that we're used to. So yeah, you need some sort of stuff to kind of define the speed of how fast stuff goes through that. Um, I said stuff too many times, so let's make some drawings to make this make sense. Actually, can you guys see that little grid back there? Those little gray dots? That's perfect. Look at that. God made me a preformed lattice. Okay, so see these little dots here? They're very periodic and they're very ordered and they look a lot like a solid. We're not interested in solids today. We're interested in fluids. We're interested in things that do not have a perfectly periodic order. Um, there is, in fact, a well-defined speed of sound in solids, but you don't really get sonic booms in solids because the solid just breaks, right? Whereas with liquids and gases, they act a lot differently when they're under stress. But we'll get there. If you think about a piece of styrofoam, this is a solid, of course. It doesn't look like that. It's actually a bunch of polymers, and it's an oil derivative, I think, polystyrene. It's not ordered like this. It's not like quartz. It's not like corundum. It's not like a crystal. It's like the molecules are actually all over the place. But the point is, it's a solid. So when I stress it like this, it deforms a little bit. Now, this deformation is known as elasticity. So something that's compressible, see how I can make it expand and contract? Something that's compressible like styrofoam is not a universal property of matter. You have things like water and air, which are theoretically incompressible. That is, if I had water and I pressed on it, nothing would happen. The water would just exert outward pressure to contradict the pressure that I'm putting on it. So it's the water doesn't deform. Air doesn't deform when you put pressure on it. So in actuality, it does. But a lot of times we idealize and call these things incompressible media. And an incompressible media would be something like much harder, like plastic. If you think about water, imagine water and put like some water in your hands and then do this. Okay, it just sprays out all over the place. It doesn't do that. So that's what I mean by incompressibility. So we're interested in things that are theoretically incompressible. Mostly air and water are going to be the places where we're going to define some sort of speed or something. And what's interesting about styrofoam is when you deform it too much. Like let's say something goes through it, or I just put too much stress on it, it breaks, right? What that breaking actually is these, again, pretend we have like quartz and I broke quartz or something. These guys have little bonds in between them. Every single one does. And we have two atoms with a bond, or molecules in the case of polystyrene. And this is, let's say, their equilibrium point, and I pull them out a little bit further. And this bond gets a little bit longer. So what that bond is doing is deforming. This is the essence of compressibility. Things that do that are compressible. Things that do not do that are non-compressible. They're incompressible media. Water, the H2O molecules, if you push them apart, the bonds don't do anything. The molecules stay bonded at the exact same distance to each other no matter how much pressure you put on it. That's not true in reality, of course. If you detonate a bunch of TNT underwater and create an explosion, you'll see that water is extremely compressible to the point where it will rupture your eardrums and maybe kill you, depending on how far away you are. But in physics textbooks, we say water is incompressible. What that really means is it has very high rigidity. It's very resistant to compressibility. Whereas that styrofoam I just showed you likes to compress. Think about a spring. That's kind of the ideal compressor. It's something that when you pull in and out, the atoms or molecules move further away from each other so that the entire rigid body stretches. That's what compressibility means. When I put stress or pressure on something that's compressible, these bonds get bigger and bigger, further and further away from each other, until at a certain point, the bond no longer has enough force to overcome the pressure I'm putting, and it breaks. The bond breaks. You can think about this, for example, the moon rotating the Earth, around the Earth. If you put enough centrifugal force on the moon, it will just fly off. It's as simple as that. It's just another type of bond that we're putting stress on, pushing it away from equilibrium. And at a certain point, the force I'm exerting is going to be less than the force that the bond can actually put on to compensate. So at a certain point, it's going to break. And there's a class of fluids called simple fluids. And they're essentially fluids that do not have this property of elasticity that I've been talking about. A simple fluid is water. You think of water as incompressible, it doesn't have elasticity to it. The opposite would be something like tar. Tar is very elastic. If you have some tar like this and you pull it apart, it stretches. Stretching is kind of what elasticity looks to us at the macroscopic scale. So if I have some water, can you really stretch water if you think about it? No, not really. It just kind of flows. So the idea is these simple fluids like water, they don't do what styrofoam or tar does, because if you pull tar silly putty enough, it snaps, it breaks, right? Like a rubber band. Water doesn't do that, or so we thought. There was a very recent finding that was forwarded to me. I think Drexel and ExxonMobil get credit for the discovery, but they were working with some sort of petrochemical. I'm not sure what it was. But anyway, they had it like in this tube in like a cylinder, and they had these pistons on either side that were pulling opposing force on them. And kind of pushing it back and forth and back and forth and back and forth. And they do this because in oil wells and oil machinery and things like that, they have to know the properties of these fluids. Otherwise, the pipe will do unexpected things and the machinery will do unexpected things. So it was just a routine thing. But what happened was they heard this loud snap in the lab. And they looked, and they were kind of confused because it was a simple fluid. It didn't have elasticity, theoretically. And yet it snapped the way that a rubber band or a spring or a piece of styrofoam would snap. And this actually contradicts a very long-held belief in fluid mechanics that simple fluids simply can't do this. So this is really interesting. And the reason it was forwarded to me is because this is kind of the very, very high viscosity limit of what we see in air with airplanes, which is a sonic boom. I can't talk about specifically why this article was forwarded to me. I have two uncles that work at Lockheed Martin, and the other one works at Hughes Aircraft. So you probably use your imagination, but the idea is that this is a very high viscosity limit of a sonic boom. So it's interesting to me from a fluid mechanics standpoint, professionally, academically, and intellectually. And we're gonna talk a little bit about how the phenomena kind of dovetail, and we're gonna get an abstract, big picture view of the phenomenon of a sonic boom or a fluid breaking, and how they're actually pretty much the upper and lower limits of each other. They're two sides of the same coin of the same phenomenon. And what is this phenomenon? It's essentially we have this material. You can imagine the gray little lattice, whatever, and it has a speed. That it's called the speed of sound. And the speed of sound is basically if I poke the medium here, how long does that take to affect a piece of the medium here? That's called the speed of sound, and it's different in every material. So the question is, what if instead of in a lab poking the material here and then waiting for it to propagate and then measuring what happens here, what if I start poking and prodding much faster than the material can respond? That's when you get a sonic boom. An airplane flying faster than the speed of sound will be perturbing the air faster than that perturbation can propagate throughout the air to other regions of that air. That's why you get a sonic boom. What essentially happens is you're perturbing the air here, and all these pressure and deformations of these bonds that I'm talking about, they're storing kinetic energy and they're building up. And essentially they're creating waves. In other words, you poke it here and it goes here, and then it goes there and it goes there and it goes there. As time goes on, it travels further and further out. That's essentially a wave. It's a periodic phenomenon. So when I'm continuing to disturb the air and it can't propagate fast enough, and I'm still disturbing the air more and more and more, these pressures and deformations and energies build up and up and up. And rather than simply dispersing as regular pressure waves, like sound is just a pressure wave, I basically poked an air molecule here, and the deformations in the bonds have kind of propagated throughout the air over to my ear. It's a normal sound. But with a sonic boom, you're creating sounds and perturbing air at different points in the air faster than the air can keep up with itself, which is why you get a buildup of pressure, and these pressure buildups create these waves, and these waves we hear on the ground as a sonic boom. So when you're dealing with a much higher viscosity fluid than that. And viscosity, let's define that here. Um, so I've essentially just defined the speed of sound in a fluid, right? So um, I was doing some GRE prep before, and there's like a linear algebra problem, and it's actually been so long since linear algebra for me that I actually forgot like the orthodox standard formula way for finding eigenvalues and eigenvectors. So what I actually did was literally I just said, well, I mean, I know what an eigenvector and an eigenvalue is, right? So like it's literally just a vector that you do like that, and it's going to give you back some constant times a and b, right? So like I literally just set these things equal to each other, and I kind of just figured it out from scratch. So that's the kind of approach I want to use with talking about supersonic phenomena in materials. I don't want to come at you like a textbook with things that people already discovered in the order that they discovered them, kind of prepackaged and put in a nice way to be intuitive. What I want to do is I want to imagine that we are aliens who have never seen a fluid before. We've never seen any kind of matter. And I'm basically sitting here explaining to them um, when scientists first started playing around with fluids, what things they were curious about. So the first thing we already talked about, which is the speed of sound. That is, if I poke the fluid over here, how long does that take to disturb the fluid over here? That's the speed of sound. It's something we naturally be curious about. There's another thing we might really want to be curious about too, which is if we have this fluid medium, right? We have like a liquid, and I haven't really said what a fluid technically is versus a solid. A solid has this periodic ordered arrangement. A fluid is kind of sloshing around, and the distance between the molecules relative to each other is changing continuously. So it's just like a bag of stuff sloshing around. That's a gas or a liquid. And in a gas, there's basically no attractions between them. There's no bonding. Whereas in a liquid, there are collective correlations because these bonds do actually communicate with each other. But the fact of the matter is, you have this stuff sloshing around. So you poke it over here, and maybe you push it to over here, right? And then you're curious, maybe how long is this fluid going to take to relax back to equilibrium? So how long is this going to take to come back to here? If it does at all, that's an open question, but it does because these are harmonic oscillators. So mathematically, yes, it does relax to equilibrium. The question is, how long does that take? So if I have like some honey and I poke the honey, how long does the honey take to relax back to the way it was before? And from this curiosity comes the concept of viscosity. Viscosity is how thick a fluid is. Honey is very viscous. Water and air are not very viscous at all. So this concept of viscosity is something that air really lacks, whereas fluids like the one that was in the ExxonMobil lab, that was a much more viscous fluid. So when you pull it apart, it can actually break. So the question is, if I have this fluid or liquid or whatever, and I start pulling the bonds apart to the point where the force of the bond can't counteract the force I'm exerting on anymore, and these bonds break, what happens then? That's the interesting question. What does happen when that happens? I just told you what happens in air. You get a sonic boom. But what if the viscosity is much, much higher than air? What happens then? Well, it's quite interesting. You can have a couple of things happen. So we have these molecules, and you can't really just pull one molecule in a fluid because they are all bonded to each other. So we get these collective excitations. When we pull one, that bond pulls on another and another and another. Eventually you get this kind of region or volume within the fluid that has a certain pressure exerted outwards on it to the point where the bonds can no longer hold, and two things can happen at that point. One, you can get an actual true vacuum. That is, you can pull apart these molecules, the bonds break, and there's literally nothing there in that cavity at all. That's called cavitation. That's a vacuum cavity. Or what's possibly more interesting is you have something like water. And water, if you elevate it to a certain temperature, will boil. But did you know that if you reduce the pressure enough, it will also boil? So when there's enough of a pressure gradient on the outside of this volume versus the inside of this volume, what will start happening is that this liquid fluid will actually start vaporizing in small localized regions. And you'll actually get these kind of pockets of vapor. So yeah, um, it's a frontier. It's a frontier thing. It was just discovered. So like I can't give you the same level of detail as I can about like the sonic boom because we don't know. This hasn't been very well studied yet. But it's quite fascinating, and that's basically the phenomenon um, that that I want to talk about. And so I've given you kind of the naive, I've never seen a fluid before. I'm just a curious scientist. Let's discover physics kind of perspective. And in the next lecture, I think, and then I'm going to go and be quantitative, and I'm going to give you kind of the textbook thing. Pretend that the curious scientist has kind of done his job and found all these things out. Now he's coming to you as a student in a physics class, and he's going to explain what he found. The standard way we learn physics. I started with this way because it's much more exciting. But of course, we do need to get to the other one if we're actually going to be able to, like, build stuff and work in labs and stuff like that. So we got to know the equations, and we'll do that next time. Cheers.